So let's learn about the energy level, the principal, the sublevel, and then the atomic orbital a little bit more in depth. And then we will learn how to write something called electron configurations, which is what ultimately this exercise is all about. So we know already that the original Bohr model had those energy levels, the quantized levels where the electrons would jump to higher levels when they absorb energy and then come down to lower levels when they relax. And we gave them an abbreviation, a lowercase n. N was given value starting with n equals to 1, n equals to 1, 2, 3, 4, 5, and so on. Now within each of the value of n there are sublevels, but n itself, the higher the number, the higher the energy. Please keep that in mind. So when I say n equals to 1, that's a lower energy principal energy level. Then n equals to 2 is more higher in energy than the n equals to 1 level. So within each of these levels there could be sub-levels, and previously I said there could be anywhere from 1 to 4 sub-levels, but let's give an exact number. It's going to be different for each principal energy level, but it's very easy to figure out. When n equals to 1, there is only one sub-level. When n equals to 2, there are two sub-levels. And you may have guessed what would be the number of sub-levels when n equals to 3. That's right. When n equals to 3, there are three sub-levels, and so on. How many total electrons are possible within any energy level? Let's give a number to that, and it's very simply found by squaring the value of the principal energy level and multiplying it by 2. So if n equals to 1, that's our principal energy level, then 1 square is 1, and 1 times 2 is 2. There can only be 2 electrons within that level. So when n equals to 1, there are only 2 electrons that are possible. There could be less than that depending on which atom it is, but not more than 2. When n equals to 2, that's going to give us a value of 8 possible electrons we can have. What happens when n equals to 3? 3 3s are 9, 9 times 2 is 18. 18 possible electrons. What happens when n equals to 4? Pause the video and ask yourself. If you said 32 electrons, that's right, because 4 square is 16 and 16 times 2 is 32. So those are our principal energy levels, and like I said, each principal energy level has certain number of sub-levels. When we are in n equals to 1, we have one sub-level, n equals to 2 has 2, n equals to 3 has 3 sub-levels, n equals to 4 has 4 sub-levels. What were those sub-levels? Sub-level is a set of energy equal orbitals within a principal energy level, and the sub-levels we previously said there are 4 of them, given the abbreviation lowercase s, p, d, and f. The s sub-level is lower in energy than the p sub-level, followed by d, followed by f. That's why I stated them in this order. So those are the 4 sub-levels we have. Electrons in 3D subshell, for example, if you have an electron in the principal and 2 electrons, both of them are in the principal energy level 3. But how many sub-levels can there be in principal energy level 3? N equals to 3? 3 sub-levels, right? And if there are 3 sub-levels, they are going to be started from the lowest one. And so the 3 sub-levels found in n equals to 3 are the s, the p, and the d. So if you have an electron in the s sublevel and the d sublevel, which one would have higher energy? The electron in the 3s or the 3d? If you said 3d, that's right, because the d sublevel is higher in energy. What are the sublevels found in n equals to 2, and how many are there? There are 2 sublevels when n equals to 2, and they are the lowest 2, s and p. What are the sublevels found when n equals to 1? there is only one sublevel, and that's the lowest one, S. Alright, so that's how the sublevels and the principal energy levels interact. And here is the matter that we just discussed in a table. N equals to 1 has the sublevels 1s, n equals to 2 has the 2s and the 2p. Pay careful attention to how they are written. Here we see the combination of the main or the principal energy level and the sublevel. So for n equals to 2 put together we have 2s and 2p. N equals to 3 has 3s, 3p and 3d. N equals to 4 has 4s, 4p, 4d and 4f. Well, what happens when n equals to 5? Is there any sublevel more than SPDF? We do not need to worry about any of that. The 4 sublevels we have here will be more than sufficient to house all the electrons in all the atoms that we have in the table of elements, the periodic table of elements. Now, previously we talked about how from principal energy level we have the sublevel, and then we have the orbitals within the sublevel, or the atomic orbitals, which are a specific region of a sublevel containing a maximum of 2 electrons. Each orbital can have a maximum of 2 electrons, and orbitals are named by their sublevel and principal energy level. Now, what does that mean? We will soon discover that exactly what it means. Each type of orbital has a characteristic shape, and so if we have the S sublevel, the shape of S is basically spherical. It's very symmetrical. It's like a football. I mean the international football, the soccer. The P sublevel has the shape much like a dumbbell. We will look at both of them. The D and the F, we will not look at the shape, because as we progress into higher energy sublevels, we get more and more complicated shapes. But you can do a Google search and you can look at the shapes of all of them. Here are the shape of the S sublevels. Here would be 1s, where the 1 stands for the principal energy level and S for the subshell or the sublevel, then the 2s, then the 3s. One difference between all three is that as you progress higher into the higher principal energy levels, the size of the sublevels, the subshells, also gets larger. And here are the P. Now P has 3 different forms, actually 3 different orientations in space. One of it is oriented in the x direction, the other in the y direction, and the last one in the z direction. Okay, so how many orbitals are there altogether within each of the subshell? S contains only one orbital, and so basically when we talk about the S subshell, we are talking about this shape, the spherical shape, as the orbital itself. What about P? How many orbitals are there in the P subshell? There are 3 orbitals in the P subshell, and if you guessed that those are produced by the 3 different orientations of this dumbbell-like shape, then you are right. Because the shape of the S orbital is spherical, there is no orientation where you get any differences. They are all going, whether you rotate them clockwise, counterclockwise, upward, downward, you will only have one shape for a sphere. But when we rotate the P shape, the dumbbell-like shape, 90 degrees, we get 3 different orientations, and that's where we get the 3 orbitals from. So the P subshell always has 3 orbitals, and the D subshell, whose diagram, whose shapes we are not going to look, has 5 orbitals. So previously we learned that each orbital can have a maximum of 2 electrons. So ask yourself, how many electrons are possible when you have an s orbital? If you have, you have the s subshell. Because the s subshell has only one orbital, how many electrons are possible in this orbital? 2 electrons are possible here. when you have the p orbital, how many electrons are possible in the p orbital? Because I mean when you have the p subshell, because the p subshell has 3 orbitals, there are 3 times 2 6 electrons possible. And how many electrons can be found in a d subshell? Because we have 5 orbitals in the d, we have 5 times 2 10 electrons. It doesn't matter if it's 4d or 3d. So if we go back here where we looked at the possible subshells for each principal energy level, how many electrons are possible here? Because s can only have 1 orbital, there are only 2 electrons possible in the principal energy level here, n equals to 1. Now here s can only have 1 orbital as well, so that's 2 electrons in this location, 2s, but p can have 3 orbitals and each orbital can have 2 electrons, so a total of 6. With this 6 here and this 2 put together, how many total electrons are possible? 6 plus 2, 8 electrons. And remember that equation we had for the total number of electrons possible when n equals to 2. 2 square is 4, 4 times 2 is 8. So that's where we get the 8 from. 2 in here and 6 in here. Here, as we go down, 3s will be the same as 2s in terms of total electrons possible, 2 electrons. 3p will be the same as 2p in terms of total electrons possible, so that's 6 more. So that's 2 plus 6, 8. How about here? In d we have 5 orbitals, each one can have 2 electrons, so 5 times 2, 10. So that's 2 plus 6 plus 8. I mean 2 plus 6 plus 10. That's 8 plus 10, 18 electrons. And we learned that when the principal energy level is 3, 3 square is 9, 9 times 2 is 18. You can do the same thing with principal energy level 4, but I will tell you how many electrons are possible in the f orbital. I mean in the f subshell. In the f subshell we have 7 orbitals and each one can have 2 electrons. So that's 7 times 2, 14. And the 4s, 4p and 4d put together should be the same number of electrons as 3s, 3p and 3d, which was 18. 18 plus 14 is 32 electrons. And if you recall, 2n square with n equals to 4 gives you 32 electrons. So that's how we have the electrons organized between the principal energy levels, subshells and finally orbitals. Then we will look at the electron configurations, which is how we show all the electrons distributed for a given atom.